For more problems and videos like this for linear algebra, you can take a look at Sarai Studies. Link is in the description box below.
We are told to determine if B, this vector right here, is a combination of these vectors. So just translate it into an equation. So we have B. We're asking if B is a combination of these vectors. So combination means you're putting them together, so you're adding them. And they're scalars. So each vector can be scaled by some scalar. Now let's plug in what we have. We know what these vectors are. We know what B is, but we don't know what our scalars are. So the question really becomes, are there scalars that will combine with these vectors to give me this vector B? And if there are, that means that B is a linear combination of these vectors and their respective scalars. I know I have arrows over here, but just pretend there's arrows over all of these vectors here, except the C's. The C's are not vectors. They're just numbers. Now we call this vector form. Recall that anytime you have a scalar, you're really multiplying that scalar by every single thing in that vector. So this is really C1 times 1, C1 times -2, C1 times 0, and then we have C2 times 0, C2 times 1, C2 times 2, and then we have C3 times 5, C3 times -6, C3 times 8, all equal to this. And then you ask yourself, well, this looks very familiar. These look like a collection of equations. Wait, that sounds familiar. Oh, it's a system of equations. Oh, if only we had a tool that allows us to solve systems. Oh yeah, we do. It's called put it into a matrix and put it into reduced row echelon form. So our coefficients are these, and our B values are these. So now I have my matrix A of B. So then now, instead of every column being attached to a variable x1, the variables are C1, C2, and C3. Those are the variables that we are solving for. We're solving for the scalars that will combine with these vectors to give me this. And if there's no solution, that means that there are no scalars that combine with these vectors to give me this. So therefore, we say that this is not a linear combination of these vectors. This is as simple as that. So I start with my leftmost non-zero column. That's this one. My pivot position is at the top. I want to kill whatever is below my pivot position. By kill, I mean make everything a 0. This is already a 0, so we're good. This has to be killed and made a 0. So this is in row 2, so I want to kill something in row 2. I want to use whatever's in my pivot position to do so. My pivot position is in row 1. Then I set up my equation plus whatever is here, that's row 2. To find out what I need to change in order to get this to be a 0, I'm going to write these two rows down here. So row 1, row 2. Then I ask myself, what's my goal? My goal is for this to be 0. That's the first entry, so the first entry here should be 0. Then I focus on this column and I ask myself, what can I change about this so that when I do this plus this, it's going to give me 0. Why about this? Because if I'm focusing on this column, then I'm only ever going to change the value in the row that my pivot position is in, which is row 1. So I want to use the value inside my pivot position to kill this. So I want to change this so that when it adds with this, it gives me 0. Well, then it would have to be 2. So I would have to multiply this by 2, but whatever I do in one entry, I have to do to the rest of them. So this becomes 2 times row 1. So then this would become 2. This is still 0. This is 10, and this is 4. Then I just add 2 minus 2, 0, just like I wanted it to be. This is 1. 10 minus 6, that's 4. 4 minus 1, that's 3. And then this matches with this. This is my new row 2. Since row 2 is the only thing I changed, this top one and this bottom one are going to stay the same. And row 2 is going to be replaced with new row 2. So this is my pivot position. Everything below it is 0. We managed to kill everything under it. Great. Now we can move on to the next submatrix formed, which is this one. When you cross out the corresponding row and column of your current pivot position, you're left with this matrix. And so again, you start with your leftmost non-zero column. That is this column. And then your pivot position is the one at the top. Then you want to kill everything under it to be 0. The thing that I want to kill is in row 3. So I want to kill something in row 3. I want to use whatever's in my pivot position to do so. My pivot position is in row 2. I'm going to add, and then whatever is here, I'm going to put right there. To find out what I need to change to get this to be 0, I'm going to write these rows down here. Treat as an equation. Then I ask myself, what's my goal? My goal is to get this second entry to be 0, so I count this needs to be 0, my second entry. Then I focus on this column. What can I change about this number? So how can I change this so that when I add it with this, it's going to give me 0? Well, this would have to be -2. So I'd have to multiply this by -2, but whatever I do to one entry, I have to do to the rest of them in that same row. So this would be -2R2. This would become -2. 4 times -2, that's -8. 3 times -2, that's -6. So then I add, this is 0. This is just what I wanted it to be 0. This is 0, and this is also 0. And then this matches with this. This is my new row 3. Now, since the only thing I change is row 3, the top 2 rows are going to stay the same, and then row 3 is going to be replaced with this new row 3. Now I can see that we are in row echelon form because it passes the staircase hack. All 0 rows are at the bottom of the matrix. So Z, S, and then all entries under the leading entries are 0. The leading entries, all of them are 0, so it passes ZO, so it is in row echelon form. Because it's in row echelon form, I see that 0 is equal to 0. That means there's going to be many solutions. That means that there's going to be many scalars that combine with these vectors to give me B. So I already know that B is a linear combination of these vectors, just from row echelon form. But to properly describe the solutions, let's keep on going and get it to reduced row echelon form. Remember that this is row echelon form, and then reduced row echelon form is just 1C, so you're checking that all of your leading entries are 1, they are, good, and you're checking that they're the only one in that column, so everything else is 0. So is everything else 0 in the column? Yes. Is everything else 0 in this column? Yes. So this is already in reduced row echelon form. We can rewrite this back into a system, so every row is an equation. Recall that now we're solving for scalars C1, C2, C3, so these coefficients are attached to the C1, and then so on. So write down each row, so 5, 2, 0, 1, 4, and then 0, 0, 0, 0. So these are equal signs because these are our B values. So these numbers here are attached to C1, so C1, C1, plus, plus, plus. These numbers here are attached to C2. These numbers here are attached to C3. So this is what we have. When we remove the zeros, we're left with 0 is equal to 0 at the bottom. We can remove the ones. We can move things over. So these are the solutions to this system, but it's not very clear what the actual solutions are. But remember, we have something called parametric form where we can describe these solutions in a nicer way. First, we need to identify our free variable. Remember, our free variable is the variable whose column does not contain a pivot. So here we had a pivot, here we had a pivot, right? These were our pivots, but then the only column that never had a pivot was this one. So therefore, since this is a non-pivot column, C3 is our free variable. What does that mean? C3 is free to be anything it wants to be. So C3 is equal to C3. It could literally be anything. It could be 4, it could be 3, it could be 2, it could be negative 2,000, whatever. So then the goal of the parametric form is to write your other variables in terms of this one. So in other words, I can have C3 be 1. I plug in 1 in both of these, and so when C3 is 1, C1 is going to be 2 minus 5, which is negative 3, and C2 is going to be just 3 minus 4, which is negative 1. But then these scalars change every time I change what C3 is. That's why there's many solutions. I can plug in 2 and then get different values for my scalars. But the idea is that this is one of the many solutions. I can plug in 1 for C3, so negative 3 for C1, negative 1 for C2, positive 1 for C3, and when I multiply those times these vectors, I will get this. That is the whole point. So these are one of the many solutions. And so therefore we can say vector B is a linear combination of these vectors because there exists such scalars that will combine with these vectors to give you that vector B. So that's it for this video. I'll see you in the next.